So deductive reasoning is laws. Now, in the video, we covered these two here, the law of detachment and law of syllogism. Yes? Law of detachment, if the hypothesis of a true conditional statement is true, then the conclusion is also true. So with these here, they will give us a statement. They will give us a conditional statement. And if the hypothesis of that statement is true, the conclusion must also be true. So here, if two segments have the same length, then they are congruent. And what did it tell us? It told us that BC is equal to XY. BC equals XY. And because there's not a line above it, it means the lengths are the same, yes? So what it's telling us is that the lengths are the same. It's telling the lengths are the same. Well, what was our conditional statement? If two segments have the same length, BC equals XY. That's telling us they have the same length, yes? Well, yes. This here is making this part of the hypothesis, or the hypothesis, true, yes? So if the hypothesis is true, the conclusion must also be true. So it means BC equals, or BC is not just equal, but it's congruent. And we use the two lines with kind of a little wavy one above it to say congruent. And we use congruency this here to say two shapes are the same. Equality means two things are equal. They have the same value. So equal signs dealing with value. We're talking about a specific value. Equality is meaning they have a similar, they are the same shape. So they mean two different things. So questions on detachment. Okay. If it is between 9:50 and 9:50 a.m. and what do we get out of here? 10:41. Yep. a.m. Then you're in third period. It's 10 a.m. So what can we say? If it's between 9:50 and 10:41 a.m., then you're in third period. So if it's 10 a.m., is the hypothesis true? Yes. So what can we say? You're in third period, yes? Since the hypothesis is true, the conclusion must also be true, yes? Okay. I'm going to change a little bit. Let's say it's 11 a.m. Is the hypothesis true anymore? No. No. So can we say anything? No. We can't say anything. It might be tempting to say, okay, well, we're in fourth period, but no. Because the conditional statement does not mention anything outside of third period relating this time to third period, we can't say anything. It's not possible. We cannot use the law of detachment for this here because it's not possible. And that's it. Now, on the video, the other video, we did more examples of law of detachment than that. But that's it. That's it in a nutshell. If the hypothesis is true, then the conclusion is also true. So if they give us a statement that makes the hypothesis true, the conclusion must also be true. Now, if they made a statement, they gave us a conditional statement, and the conclusion was true, that does not mean the hypothesis is true. Okay? Now, if you remember back to the truth tables, because I mentioned it briefly, because truth implies false gave us false, and if you remember the false, false implies true, implies false. they were both true, it really doesn't make any sense because, again, if the hypothesis is false, it doesn't matter what happens because nothing's going to work. If y'all have done, because at this point you should have had the scientific method in biology at some point in one of your science classes, yes, forming a hypothesis and then proving it. Well, what happened when our hypothesis was wrong? We had to go back and we had to rechange it. We had to redo it. We had to restate our hypothesis because it was false, yes? This is why, because it doesn't tell us anything, okay? Because if the hypothesis is false, it proves it to be wrong, okay? And this could, so outside of the scientific method, that wouldn't be any harm, right? Well, some of you might propose eventually, yes? Find someone you love. I love you, therefore I want to marry you. I love you, therefore I want to marry you. What happens if you don't love them? The hypothesis is false, isn't it? So the whole thing is true. So it could be the case that you don't love them, but you end up. Yep. So the mathematically correct way to say it is I love you, and so I love you, therefore I want to marry you, but it's not the case that I don't love you and don't want to marry you. Mathematically accurate way to do it. But, so again, that's why we have to make sure the hypothesis is true. If the hypothesis is true, the conclusion is true. But just because the conclusion is true doesn't mean the hypothesis is. Okay? Because one, it has to go one way. We have to have the hypothesis first. Law of syllogism, this is one of the ones that sometimes gets confused. But one of the key things when looking at this here, I'm going to get a highlighter out when you're working them. If you want to write them out and circle it, or on the test you want to circle which ones match up, I do that. Because when we look at this here, if x squared is greater than 25, then x squared is greater than 20. Okay. If x is greater than 5, then x squared is greater than 25. Well, these two here are the same, yes? They're the same statement. And if, using law of syllogism, if the two that are the same is one of them's an if and one of them's the then, the two that match up, one of them's if, one of them's then we can do this by taking the if always comes first, if x is greater than 5. I didn't change anything, did there? Then what? Then x squared is greater than 20. So if with law of syllogism, if between the two statements, if an if of one matches the then of the other, take the other two and put them together. And that's it. But the two that match, and one statement has to have an if, the other has to have a then. Okay? Because the two statements that are left, one of them has to have an if, the other has to have a then. Yes?
So on the side, like on the top part, there's a tooth, but on the bottom part, there's not one.
Here?
So on the A, like where you have it highlighted, for the X, there's a tooth, but down there, there's not.
Right here? So these two are the ones that match up. It doesn't match up with this one here.
Yeah, I was talking about when you wrote it down. Can you write down the highlighted part?
No. Because the highlighted part matches. It's telling us these are the same. So if this is true, then this is true. If this is true, then this is true. So because these two match up, it means that these two will also work. So if x squared, so let's start with this one here. If x is greater than 5, so what would be a value that works for that? So let's say x is 6. Is x greater than 5? Yeah, x is what? 6. Then x squared is greater than 25. Well, x squared, 6 times 6 is? So is x greater than 5? X squared greater than 25? 36. If 36 is greater than 25, well, yes, that's true. then 36 is greater than 20. Yes, it works all the way through. So because this is the same, we can almost get rid of it and combine those two. If x is greater than 5, then x squared is greater than 20.
How'd you get 6?
I picked it. So I just picked a number to make this true. I just picked a number. It didn't matter what it was. I just so we can kind of see that. Because here it's still, this here is still true. And so the main way we write it is, okay, I had an if, match up to a then. I got rid of those. Combine the two that were left. Now let's look at this one here. So there are two parts that match up. If a polygon is regular, then all angles in the interior of the polygon are congruent. If a polygon is regular, then all its sides are congruent. So these two match up, yes? Is one of them an if and the other one's a then? No, we have two ifs, yes? Not possible. Not possible. Because for this to work, we need an if and a then statement. We need an if and a then to match up, and we need an if and a then left over. And this is not saying that these are false. These are two false, or not, these are two true statements. A regular polygon, we'll cover this more when we talk about polygons. When we say one is regular, all interior angles and all sides are congruent. Both of those statements are true, but we don't have the if-then setup. To where if I eliminated those two, I have an if in one and a then in the other that I can combine. All I have left is two then statements, yes? So this is impossible because I don't have an if and a then statement left over. So questions on this here? Okay. And we did more examples of that there because you're probably watching the video. We did multiple of both of those. I just have one and one for some reason. I added more to the other one. Using inductive and deductive reasoning. Now we're going to combine the two. They're going to intermingle. Not that we're going to use both at the same time because we can't. Because inductive is using something we see. Deductive is using facts or proof. Something that we have properties to prove. Because it's going to be one or the other. Because we can see facts, but they're facts. If I'm observing something, I'm observing a pattern. If it's facts, it's going to be facts. If it's something I can observe, it's going to be something I'm going to observe. We don't have one or the other. One trumps the other. Does that make sense? Because we can observe something that's a fact or a postulate, but really, it's a postulate, something that's been proven. So what can you conclude about the product of any two even integers? Product of an even integer and any other integer? Okay, so do we have proof of this? Y'all know a proof or a fact about the product of an even integer and any other integer? No, so let's try some stuff. 2 times 1. 2 times, so Caleb, give me a number. Let's try two even numbers. 2 times 4 is? How about 2 times negative 2? It's still even, yes? So the product of an even number and any other integer is always an even so 9.9. 2 times 9 is 8, carry the 1. 19.8. So what would we say about this? What is an integer? Positive or whole, or positive or negative whole number. Decimals 19.8 there is rational. It's a rational number. Anything we can write as a fraction. So 19.8 would be 19 and 8/10 or 4/5. If we can write it as a fraction, it's rational. Integers don't include decimals. So that's where they get that stipulation and kind of pull that out. And we could consider it even because it's divisible by 2. So this case wouldn't count because it's not a integer. But yeah, that's a good thought. That's a good thought. I like it. We could, but then we still wouldn't be using integers. Let n and m each be any integer, then use deductive reasoning to show that the conjecture is true. So we showed it using inductive because we used examples. So let n and m be any integer. As it's going to be n times m. Okay. So any integer, so we want to prove this here, yes? So if I do 2 times n, I'm going to get an even number. Because it's going to have a multiple of 2, yes? So if I do 2m is going to be even, yes? Mm-hmm. And then we could pretty much say 2mn is also going to be even, or really, 2n is an even integer because any integer multiplied by 2 is even. 2nm represents the product of 2n and any other integer m, because we're treating 2n as a number itself. And 2nm is a product of 2 and an m, so 2mn is even integer. So this wasn't something hugely important, but it's another way to go about proving this if we're going to use deductive reasoning. So we need to use more facts, not just examples of any number, or just set numbers like we did here, because I just picked numbers and showed it. Here, the main difference is that m and n are any integer. So I just defined it on any number we could possibly plug in for m and n, but it's going to be even. So these are a little bit harder to do. Comparing inductive and deductive reasoning. So we're comparing the two. And this is kind of the last few things we'll do here. There's not too many examples because I feel like this is, hopefully y'all are getting this and understanding it. So when we look at this here, decide whether inductive reasoning or deductive reasoning is used to reach the conclusion. Explain, and then we'll explain. Each time Monica kicks a ball up in the air, it returns to the ground. So the next time Monica kicks a ball up into the air, it will return to the ground. Is that inductive or deductive reasoning? So a little bit, but what are we doing? So each time Monica kicks a ball up in the air, it returns to the ground. So is that a fact? So we're talking about kind of gravity and whatnot. But did we talk about gravity here? What are we saying? Each time Monica kicks a ball up the air, it returns to the ground. Is that something we're watching? Because we're watching each time she kicks it up, it returns to the ground. So the next time Monica kicks a ball up in the air, it will return to the ground. This is what? Inductive. We observed it. There's no facts. There's no postulates. There's no proofs that are defined in this. And it'll make more sense on the next one because I believe that's going to be deductive as a hit. But this is inductive. Each time she kicks the ball up in the air, it returns to the ground. Because each time she does it, this is happening. So the next time she kicks it up the air, it'll return to the ground. That's inductive because we are observing it. It is something that's happened on a base by base situation because each time it happens, this is the result. Each time she kicks it, this is what happens. Now, let's look at this one here. All reptiles are cold-blooded. Parrots are not cold-blooded. Sue's pet parrot is not a reptile. I do not know that one off the top of my head. But let's look at this here. All reptiles are cold-blooded. Is that something we observe? No, that's a fact, isn't it? Parrots are not cold-blooded. That's another fact, isn't it? So this here is, this is deductive. Why? It's based on facts. It's deductive because it's based off facts. That the parrot is, all reptiles are cold-blooded. That is a fact. Parrots are not cold-blooded. That is just a fact, yes? Since we're using facts, it's deductive. So we look back at this one here. Each time Monica kicks a ball up in the air, it returns to the ground. Are we starting to see the main difference between the two? Because it's very tempting to say, well, obviously we know that it's going to return to the ground. That's a fact. No, that's us implying our knowledge or our beforestanding, our kind of knowledge that we brought into this, that gravity is going to pull it back down. Yep. We're good? Thank you. Yeah. So that's the main difference. If it is set facts, it's deductive. If it's something we're observing, each time this happens, or when this occurs, this follows. When this, then that. Deductive. It's pretty much this is always the case. This is the facts. This is what they are. And that's it. That's all we're covering with this here.